We are talking about predicting reaction products. So we're going to predict the products, and then we're going to actually also balance the equation. So we can't hit all the types I found out today. This turns out to be at least a 2-day thing. All right. But type 1, you got to start somewhere. Maybe this is the first one. You could kind of start at a few different places, but and I would take some notes. Synthesis means creating. So a synthesis reaction will create a new thing out of other things. And generally what we mean is that metals and nonmetals will form an ionic bond. And that is a plus minus pair. Maybe you write that in. And so it will combine into a new ionic compound. And so what I mean by this is we're going to have to make the charges add to 0, which is a thing we already even had a quiz on. So to remember to look at the charges on the cation, and that is the positive thing. And the anion, and that is the negative thing. To determine the formula of the product. So here's our example. And let's pretend we don't know this answer. Let's pretend we don't know this, and we don't even know this. I'll just cover this over for a moment. We'll pretend we don't know that. Okay. So you're going to want to, I forgot to say, you're going to want a periodic table and an ion chart. I should have said that, so I guess I got to hit pause and say, hey, go find that. Sorry. Okay, so you have, this is tin. I know that doesn't look like tin. Sorry. Remember that some of these metals have been used for like 5,000 years, and the symbols here come from the Latin. So some of them don't match English. Tin and chlorine. Also, you might remember, chlorine has the star in it. If you're using my periodic table, and the star means it's diatomic, and that means when you leave it on its own with its own kind, it likes to make pairs. So it's in pairs. So we have two things apart. What's the only thing that we could do? We could put them together. So let's put them together. But tin is here. And down in here, not in column 1 and 2, through here, I don't know the charges just by looking, so I'm going to look it up here. And tin turns out to be +2 or +4. Oh yeah, I got to type in here, use tin 4. We'll just pretend we know that, sorry. Use tin that's +4. Okay, let's pretend we know that. So let's take tin and put it together with chlorine. Tin is going to be a +4 because they told me to use a +4 kind. All right. Cl is a -1. All right. And again, all we could do, if they're apart, if you just have this apart and this apart, all I can think to do is put them together. Tin is a +4 because they told me to use the +4 kind. Cl is a -1 because it's in this column. And here's the part where we already covered this. The charges have to add to 0. So I'm going to need 4 of these. And look, I generated that. That's why it's that, because this is a +4 and this is a -1. Questions so far?
For the number 1, can you like repeat the process of this?
Number 1?
Yes, please.
I'm not
Sorry, I was printing out the periodic table because I ended up losing my old copy. And
So I'm
so,
doing the example actually at the moment.
oh, yeah, you were doing the example, but then I was busy doing something while you were doing the example, so I didn't get an
Okay.
explanation.
That if you take 10 and shove it together with, okay, here, I'll back up even farther. I have two things that are separate, and that, arrow, and pretend we don't know this part, right? For a moment. What would be after the arrow? Well, I mean, how should I know? Well, you have two things that are separate. All you could do is put them together. I mean, you can't pull them apart more than apart, right?
Yeah.
So if you have, two magnets, all I can think to do as a change is put them together. So let's put these two together. And if you pretend that it says use 10 +4 version, because I forgot to say that. All right, then we know that this is a +4. 10 is a +4, and chloride likes to be -1. So we get +4 and -1, but this is where we have to pull in previous information. Like I said, this is the unit where we start to pull in previous learning. The charges have to add to 0, so I'm going to need 4 of these so that I have 4 -1s and a +4, and that makes the charges add to 0.
Okay, and that's how you get so the answer would be SN and then Cl4.
For the product, yes.
And then that's how you got it because you needed the 4 -1s to even out with the +4.
Yes.
Okay.
Okay, which leads me to another thing that I had to hit really hard last class. So then some kid says, that doesn't make any sense because this was 2 and you said 4. Okay, and I do understand the confusion, but also this. As much as we say this likes to do that and this wants to do this, and these two are friends and all kinds of stuff like that, right? That makes them sound like people. They don't actually have brains and they don't actually know where they came from. So if I just said you have a trillion of these and a trillion of those, they're not actually smart. They don't actually know where they came from. So if you just had a bunch of this and a bunch of that, how would they arrange? They would arrange like this because that makes the charges be 0. But there was 2 of them. I'll deal with that in a minute. What would nature make if I said you have a trillion SN +4s and a trillion CL minuses? What would you get? And by the charges adding to 0, you need to say I would get this. This is what nature would make, and you don't get to say, but this is a 2. But this is what nature would like to make with this, because this makes the charges add to 0.
So you just discard that 2 because it wouldn't make anything add to 0?
This,
Yeah, you just got rid of that 2.
I'm not going to get rid of it. I'm going to say that I'm going to say if you had a trillion of these, and let's pretend does this like to break up? Yeah, it does. It likes to be CL -1, doesn't it?
Yeah.
I mean, it also likes to be that. So, okay, can I break this up? Yeah, sure you can. All right. So if you had a trillion of these and a trillion of CL -1s, what would you get? That. But it came from, nah, we don't get to ask that yet. What would nature like to make? This. But it came from, shut up with that for just 1 minute. We'll get there in a minute. What would nature like to make? This. Having said that, then we had to address the kid's point. Now let's let them speak up. But this was 2. You're right. That is 2. This comes in pairs, and yet this is 4. So how many pairs would you need to get 4 of these? 2 of them, huh?
It looks like the stuff we did yesterday, but then like the SN +4 and then CL minus and then 4 under that.
This stuff is the stuff we did back on the ionic bonding. And then the 2 pairs makes 4 is what we did last time, yeah. And then how many SNs, how many tins did we use? Just 1? Okay, I only needed 1. And so now we've got something that is a scientific true statement. These two like to make this. And if they like to make that, how many of these did it take? It took 1 of these and 2 of those to make 1 of that. So would somebody else like to speak up and say, but what about, or you said the thing, or I don't get it with that part there, or something?
Can you just show how to solve number 1? Because think I'm understanding it, but also
Okay.
not at the same time.
All right, that was my next thing. So I have 2 things that are separate. What could I do? Well, I can't separate them again. That's not a change. Let's put them together. That's a change. So let's put Zn, and again, these diatomics are able to split up. So, and how do I know that? Well, because we did say F likes to be -1. Okay, so F is a -1. Okay, sure. And then zinc, if you look around it, zinc is down in this section down here where the charges aren't obvious. So you grab this and you go zinc, 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 zinc. Zinc, oh, likes to be +2. Okay, sure. Zinc likes to be +2.
Hey, Mr. Swain.
Yeah.
That page you just pulled out with the one where you looked at the zinc, what is that called again? Because I lost it and I can't find it.
It's posted as the common ion chart, or I think the common ion chart. It's on the post that has the periodic table in Classroom. I think it cuts off the names sometimes, so I'm not sure that it displays the word common ion chart, but I think periodic table shows up.
Okay, thank you.
Oh, yep. So, zinc, there we go. There's our person back. Okay, so F likes to be -1. Zinc likes to be +2. So I've noted that. So do they know where they came from? No, they don't. So if you had 1 trillion of these and 1 trillion of those, how would they arrange themselves? Mentally, just cover this over. But they came from, that's not the question. What would they make? Because they don't actually know where they came from. So if you have +2 and -1, you would get that.
Because they cancel each other out.
Because now the charges cancel each other out to 0.
Okay, there we go. Now I understand. That actually helps a lot. Thank you.
Yeah. And then we can say, but where did they come from? Let's balance it. Oh, it already balances. This one was the super easy baby step. This one's already balanced, so you're done. That's it. And 2 and 3 are actually pretty easy, a lot like this one. So how about we go to 4? I have 2 things that are separate. What can I do? I could put them together. Okay, let's put them together. Lithium likes to be +1. Bromine likes to be -1. So +1 and -1. And again, they don't know where they came from. So let's mentally do this. If you had a +1 and a -1 and the charges need to add to 0, what do? Well, in this case, you leave it alone because they already add to 0.
That makes sense. Thank you.
And then, good. And then some kid says, but this is a 2, but that's a 2. You're right. Now that we got this set up, we can say, you're right, that's a 2. What about that? You can't take 2 bromines and claim that it only turned into 1. Are you magical? Did you destroy an atom by magic powers? No. So if there are 2 going in, 2 must come out, and I'm going to do this wrong. Do not do that. I get a lot of this. No, that doesn't add to 0 on the charges, but there were 2 of them. I know, but the way you wrote it doesn't make the charges add to 0. We can do 2 there though. And what we've said then is like this, 2 of these like that. And look, 2 bromines. 2 bromines go in attached, 2 bromines come out. They're just attached to something else, but they didn't disappear by magic either.
2 questions. First one, how the bromine, those equal 2, but the lithium, you added another one.
Right, that's the next step. Right. So, as we said last class, when you balance one thing, you often messed up something else. So, by fixing the bromine, I messed up the lithium. But now you have the lithium only 1. You're right. So let's fix that.
I forgot that you could have done that.
Okay.
And like how you were saying with how you were doing it incorrect to begin with, how it was the 2 under the bromine? Isn't that what you did for number 1? The 2 under the...
No, but that was, remember, +2 and -1, so I had to put 2 here to make the charges add to 0. This, from this one, the charges already add to 0, so putting a 2 here messes it up.
That makes sense.
Okay. Questions are good. Is there something else about number 4 I should go over? So I'm going to say tiny bit of self-quiz that I'm going to give you a jump start on. That's silver, by the way. I know it doesn't look like it. It took me a long time to remember that. But if we have 2 things apart, what can we do? Put them together. Okay, silver's and you wouldn't need to remember this, it's a +1. Silver is a +1. And oxygen can split up, those diatomics can split up, and it likes to be a -2. So tiny self-test, you don't have to admit it. If your paper catches on fire from all the mistakes you made, it's okay. You don't have to tell me. Can you finish that? Number 5, just take a minute and try that.
I was really confused by it, and I think I got that.
Okay. And if you want to tell me your answer in a moment, okay, let's just give everybody else a chance to think. If you have an actual question, like, wait, what about? How do I do? Then go ahead and speak up.
The chat's private, so would that work as well?
I didn't understand that. What?
I said the chat was private, so would that work?
Oh, you want to send your answer? Is
Yeah,
that it?
but well, you know ahead, so then you know to like check the chat. Because I know how you said you don't get the notifications.
Right. I'm just saying, if you're just going to send your answer, you can just, I mean, I don't care if you do, but we're going to give the answer anyway. But
Mr. Swaney.
Yeah.
Does it matter what order you put it in? Like, is
The
it
plus
community?
minus? The plus
No,
minus?
like when you just have, say, hydrogen plus oxygen. Does it matter if it's like oxygen plus hydrogen or hydrogen
Right.
plus oxygen?
No. Whoever made this up, because I stole a lot of this and then rearranged it, you know. That's how I got a lot of these is that and then I added this part. Actually I stole this out of somebody else's and then put that in. But no, you very much could say O2 plus AG.
Aye.
The only reason that they did it this way, and it is not a good reason, it's just the reason is because then kids might recognize that just like subconsciously that this is going to be the positive because it's on the left. But honestly, they shouldn't have to, because you should be able to say, AG, where's that? Eventually you find it, you say, oh, it's in the metals. Metals like to be positive. Oh, that's another thing. Do you need to write this down somewhere, somebody here? The metals like to be positive. If you said, oh yeah, really? I would write that down. Metals go positive. Metals go positive.
All metals, or are there like
All
exceptions to
metal.
that? Or-
No, I good question, because I keep saying, oh, except for this and except for that. Metals go positive. Yeah. So they could have written like this, and we could still do this. Okay, so you mentally self-tested and you said, oh, +1 and -2, that means I need a 2 here so that the charges add to 0. And then we can say, well, if that's what nature likes to make, how would this balance out? Well, you can't put in 2 oxygens and get out 1, and you can't put in 1 of these and get out 2. Both of those are impossible, and you're not magical. So which one do you want to fix first? I don't know. The oxygen? Let's put a 2 here. And that 2 multiplies through. Do you need to write that down? That the 2's in front, the coefficient, multiply to the whole chemical? And so somebody shout out, what goes here?
A 2.
No.
A 4.
I have 2 sets of 2 silvers. Each one of these has 2 silvers in it, and I have 2 sets of that. I have 4 silvers. Pause for thinking. Does that work for you? You should speak up if you're saying, wait, what about the thing? Or what do you mean 4?
Why is there a 2 in front of the second set of silver?
Yeah, that's what I was gonna ask.
This?
Yeah.
Okay, let's back up. Let's pretend it's not there yet, right?
Yeah.
Okay. And I mean this in a nice way. I'm really asking, do you agree that there should be a 2 here?
Yeah, because it would even out the charges.
Okay. Okay. We agree on that part?
Yeah.
All right. So at the moment, though, before I fix it, this is a scientific lie. This is not possible. It cannot be true that you put in 1 silver atom and yet you have 2 here. Where did the second one come from? Are you magical? Did you invent a silver atom? No. And if you put in 2 oxygen atoms and it turned into 1, did you destroy one by magic? No. So there must be a way to balance this so that it actually makes sense in nature. If you're going to put in 2 oxygen atoms, you had better get out 2. Now they can rearrange. Of course they rearrange. But there can't be 1 of them. There have to be 2 of them.
And how exactly do we know that there's only 1 oxygen atom?
Because there's an invisible 1 here. That's what blank means.
Oh.
Oh. Okay, I'm glad you said that then. Well, here's the thing. And then some kid says, well, I thought, no. And I've actually had kids occasionally say, nuh-uh, empty is 0. That's why it's empty. Well, and I go, really? Are we going to write down everything that we don't have? You want to spend the rest of the school year writing out stuff we don't have here? I mean, we're not going to write down the stuff that's 0, right? So by putting it, you mean you have at least 1, don't you?
Yeah.
And you can put a 1 there if you want. I don't care. Go ahead. But blank means 1. Does that work?
Yep.
Okay. Did somebody else have a point on this so far again? So if you put in 2 oxygens and get out 1, that can't be true. And you can't put a 2 here or it'll mess up the plus minus adding to 0 part. So let's put a 2 here. And that means effectively you have this. There. This is another way of writing that. So I have 2 oxygens and 4 silvers, 2 sets of 2. So now the oxygens work. 2 go in, 2 go out. But like we talked about last time, when you fix one thing, you often mess up another thing. So just keep fixing, keep working. But now I have 4 silvers. Okay, fine. You have 4 silvers. 2 sets of 2 or 2 sets of 2. I have 4 of them. Okay, but I can fix that. There. If you're going to get out 4, you must have put in 4. You're right. You must have put in 4. So let's put a 4 there. Thus, sort of concludes the synthesis section. In other words, I don't have another trick or anything for this. I don't have any other real new information. So, anybody got a question just in general about anything above here?
Not at the moment. Thank you.
And it only took us about 35 minutes. That's not a comment on you. It always takes a while the first time. I'm pausing because sometimes if I wait a moment, I get another question. Since I didn't get one, I would like to talk about single replacement because actually I think I should rearrange this so this goes at the end. But anyway, we'll just skip it for now. So in a single replacement reaction, a metal will replace another atom with a positive charge because metals like to be positive, right? So it will replace another positive. Use your periodic table to determine what charge the new metal is most likely to have. And then actually, oh yeah, there are some cases where there are, this one at least, there could be multiple answers. And honestly, I don't remember what type 2 metals even is. I think that's the stuff down here. I obviously copy and pasted this from somebody else's sheet. I'm just going to kind of mentally do that anyway. So how about we do 14? So I have a metal. How do you know that's a metal? Well, because it's in the alkali metals column. Oh, it likes to be +1. How about we jot that down? Okay, yeah, that has to be +1. And then we have iron with something. Oh, what's that? Well, it's in our groups. So that's why you have one of these. I bet its name starts with B because it starts with B. It's bromate, and the important part for right now is that it's -1. I'm going to make a note to self. That is a -1. And what's the charge of iron? Well, iron could be, oh no, it could be 2 or 3. Okay, well, that doesn't help a whole lot. But I can figure it out. But let me back up. I have this single and this pair. What?
Iron's a type 2 metal. I looked this up on the internet. A type 2 metal has 2 possible charges. So basically what it's telling you to do is just pick one.
Right. Well, on this one, we might have to pick one. Actually, on this one, we can figure out what kind this is. Okay. Here's my fundamental point, though. I have a single and a pair. So what could I do? I mean, if something's got to change or it's not a reaction. So I could put this in and grab one of these, I mean, that could happen. I guess that, I mean, I can't think of anything else. I'm really kind of asking, can you think of something else?
No.
I can't think of anything. This could grab one of these. Okay, now let me say this. I know the kids that have been absolutely just picking their nose and doing nothing when they tell me this one. This is the one that makes me yell at papers. They say, "Oh yeah, don't you grab something? I'll put this on that." That that makes my skin crawl because that is a positive, and you know this is either a +2 or a +3 because it's on the chart. Plus, this is a metal on metal. You know this has got to be a positive something. And positive simply cannot stick to positive. It cannot be done. There isn't an exception. Take that and trash it. This is a garbage answer. So do you need to write that down off to the side? This is a giant no. In fact, it reaches the level of, oh my gosh, where have you been? So if sodium likes to be a +1, what kind of thing would it attract? It would attract a negative thing. So let's give it the negative thing. That could happen. And that, we looked it up, is a -1. Okay. And then the charges need to add to 0. And then some kids shouting, they already do. You're correct.
Isn't that -3 with a +1?
I was wondering if somebody was going to say that. No, here's the way to view it. Every year I get that, and I know what you mean, but here, view it like this. This is the group that, and it as a total is -1.
Okay.
Okay. So, having said that, good point. Questions are good, right? The charges already add to 0. So let's just leave it. And then, of course, and this came up last time, somebody says, but there were 3, but you're cheating, there were 3. Well, I'm not cheating. You do have a point. For all the kids shouting, but there are 3 of them, you missed it. Oh, you messed up. I didn't mess up because they don't know where they came from. Let's mentally do this. If you had 1 trillion of this and 1 trillion of that, and the charges have to add to 0, what would nature make? They don't know where they came from. You don't get to peek in here and say, but it came from, no. What would nature make with a +1 and a -1? It'd make that.
I don't get your analogy if you say if you have 1 million of this, 1 million of that, where it came from.
Yeah, me neither.
I get people saying, but there are 3 of them. You can't have just one. Take a trillion of these and trillion of those, and and break them up into their groups and sections and pieces, and just let them settle. Just give them a stir and let them settle.
Okay,
They don't know where they came from. What would nature make with a +1 and a -1?
So all we care about is the actual equation and not the amounts of it.
We're going to balance it in a minute. Remember when we said let's make the ± pair and balance it after we get this to be true?
Yes.
Because what we need to do is make a product that nature would actually like to make. Because here's my point. Let's do it let's do this. Some kid says, no, that dumb teacher, he doesn't know what he's talking about. I'm going to put a 3 here because I was paying attention and there's 3 of them, darn it, and that's got to be a 3. But you know what you just did? This is what you just did. If you do that, you have a +1 and you have 1 of them because invisible 1 here, right? And you have a -1 and you just said, let's have 3 of them and that equals 0 and I'm done. Really? That equals 0? No, it doesn't. That equals -2. Nature doesn't want to make that. This isn't true. That 3 is wrong. So there's not a 3 there. So I don't remember who was speaking up about whatever, but does that help? And if not, speak up and ask me something else.
So basically,
So, oh, sorry, you can go.
no, you can talk. You can talk. You're good.
I was just gonna say, so at the end, like, it doesn't matter as long as it equals 0.
What we're going to ask ourselves first is what would nature make? Because what nature would make is what nature will make. And it'll make that regardless of where it came from. We're going to take these pieces, break them up like Legos or something, and then kind of throw them in the, or like magnetic Legos or something. Throw them in a pot, give them a big stir, let them settle out to what they would make. And that's what they make. It's what they make because that's what nature makes, because that's what nature makes, because nature wants it to be charges add to 0. What did it start with? That's not the point. What does nature like to make? Charges add to 0. That's what nature likes to make.
Okay.
Okay. Other person?
I was gonna ask the same thing. So
Does that work?
thanks, Nate.
I didn't see who the other person was, but does that work?
Yeah.
Okay. So this is what nature likes to make. If we agree to that finally, then the other thing to remember is don't forget to kick the iron out. Don't pretend it disappeared. It didn't disappear. I know it got kicked out, but it is over on the side. Don't just skip it. And metals can just sit by themselves, by the way. Just the one symbol. Do you need to write that down? That metals by themselves are just the symbol. In other words, they don't occur in pairs or threes or something. They're just themselves, just the one. Now we can put a number here sometimes, but we don't put a number here because metals end up just being the same thing repeated. Just a kabillion times. And each one isn't especially attached to the other one. As a matter of fact, just to go off topic just for a moment, one of the great things about metals is that they bend. And you don't build a bridge out of porcelain, do you? For one thing, it's not strong enough. But for another thing, even if it was strong enough, you got another problem. Eventually, a car crashes into it. We want the whole thing to just shatter? No. So one of the great things about metals is that the atoms will just slip past. And you can just bump this row over and then they'll just stick there. Metals are able to bend and move. The atoms will just kind of slip past each other. And that's what happens when they get dented or bent. So my point is they're not in pairs or triples or something. They're kind of just by themselves and kind of wherever they settle. So let's just put it as one. Anyway, now we can balance this darn thing. So for all the people who have been still waiting, but he hasn't addressed this 3. Okay, here we go. This is what nature would make, and we kicked out the iron and it sits here. If you're going to put in 3 sets of bromine, you got to get out 3 sets of bromine. And I think we just discussed you can't put parentheses 3 because that messes up the plus minus. But we can have the 3 here. We can have 3 sets of the thing that nature likes to make. And this is just a recipe. And also, I have a feeling somebody's yelling, you said trillions and you put a 3. Right. We're just going to get a ratio. So when we settled this here, you know what? It's like this. If you're going to use 1 trillion of this and 1 trillion of that, you're going to get 1 trillion of these. If you're going to use 2 billion of this and 1 billion of that, you're going to get 2 billion of these. It's just a recipe. How many did you really use? I don't know. It's like getting a recipe for an omelet. It doesn't tell you how many eggs you have and how many omelets you're going to make. It's just a ratio for making it.
That honestly helps a lot more. Thank you.
Okay. So if you're going to take, you can take 4 silvers and 1 of those and make 2 of those. How many are you going to do today? I don't know. You want to take 4 trillion and 1 trillion and get 2 trillion? Go ahead. And honestly, these are so small that a trillion is not even a big number. Actually, a trillion, you know what? I actually went and did the math once. And if I put 1 billion water molecules in a drop on your desk, you wouldn't notice. So when I say 4 trillion, that's not a joke at all. It's more like, and honestly, in industry, if you're actually in the business of making stuff, you might use 40 trillion and 1 trillion and get 2 trillion. So if we're going to just get a recipe for this, but if you're going to put in 3 of these groups, you got to get out 3 groups there. But that messed up the sodium. Sure, it did. So if you're going to get out 3 sodiums, you better put in 3 sodiums. And then 1 Fe, 1 Fe. Oh, that already works. So the ratio will be, you have 3 of these for every 1 of those, and you'll make, arrow, 3 of these and 1 of those, 3 of these for every 1 of those. Or, you know, and this is a concept that is very much going to come up. If you made 1 of these, how many sodiums did you use? 3. If you made 2 irons, how many sodiums did you use? 6. The ratio is 3 to 1. For every 1 of these you kicked out, you must have used 3 of those. If you kicked out 100 of these, how many sodiums did you use? 300. If you kicked out 1 trillion of these, how many sodiums did you use? 3 trillion. Now, how many did you use this week in your little process at work? I don't know, a kabillion, 11 kabillion. I don't know, a lot. But it was used in a ratio of 3 to 1 makes 3 and 1. How many did you use? I don't know. I mean, how much did you use? Whatever you used. Like a cookbook doesn't tell you how many steak dinners you made. It tells you how to make it. It tells you the ratio. It doesn't tell you how many you're going to use this week. Okay. Having said all that, is there something about 14 at all in any way that I should address or answer?
No, thank you.
Anybody else? Well, I thought 16. So I have a pair and this one. All I can think to do is take this one and grab one of these and make a new pair. Now, again, if the plus side is always the left side and the minus side is always the right side, and I don't remember anymore if I said this to this class, but if that's news to you, if you kind of said, oh, really? I would write that down. The left side is positive, the right side is negative. This must be a positive. So the answer that makes me like claw at the walls and go, oh my God, is that. Because scandium is a metal and will be positive, and cobalt is a metal and will be positive, and you can't stick a positive to a positive. So this is the I wasn't paying attention ever answer. So do you need to write that down and write down this is dumb because they're both positive? That might help. So scandium would be a positive and grab a negative. Scandium is a positive of what? Well, looking here doesn't really help me, so I'm going to go here. Scandium likes to be a positive 3. Oh, okay, sure. if you say so. Scandium likes to be a +3. And then what's that group? Oh, I don't remember. Well, that's why we have this. It's called chlorate. That's not the point right now. The point is it's -1. Okay, it likes to grab the negative thing, which is ClO3, and it is a -1. Sure. Okay, that I can live with, except it's still not correct yet. Somebody want to shout out what I need to do to fix this?
Put a 2 in front of the scandium.
No. And just in a nice way, why that? Just so I can be helpful, not to make fun of anybody. Why would that work? What makes you think of that?
I'm thinking because the 2 at the other side of the parentheses.
On this?
Yeah.
Okay. I think though we're still addressing this kind of misconception that when we're making the product, we're still looking back here, where did it come from? No. Break these up. Get a trillion of this and a trillion of this, and then remember that this can break up here, plus side, minus side, and then just put them in a bowl and stir it. What would nature make? And we don't get to say, well, what did it start with? It doesn't matter. We break it up and give it a big stir. What would nature make? Don't look over here.
Wouldn't that be even then? Because you have 3 -1s.
I don't have negative. That I'm glad you said that. And every year I get a lot of that. Remember though that this whole group is the -1.
Oh, I thought you said it was the other way around. That the top part was part of the group.
The top part was part of the group. The top part?
Yeah, how like you draw the box around it and how the top part is outside the box. They said the top part was inside the box. Yeah, the negative side.
It doesn't really matter. I think it communicates the information I want to say more if I put it outside the box. This whole thing, including the 3 oxygens, this whole thing is -1. And did I put the minus inside? I think I put the minus. In fact, I can see the little eraser. When I put a box up here the other time, I put the minus side outside. This whole thing, this whole group is -1. And I know why people. Go ahead.
I was gonna say, if in that case, then you need to get 3 of those. So you would have to find a way to make the ClO -3.
See, right. Can I just be really picky on you? I'm going to be
Sure.
nerdy. It's ClO3. So we've got to make the ClO3 be -3, right?
Yes.
Yeah. Okay. So let's take the ClO3, which is a group, mentally box, right? And let's make -1 and make it be -3 total. Yes. So let's take 3 of the whole thing, and now I have 3 sets of the thing that is -1. Now this is really key. This is also the stuff we did back on the ionic naming quiz, but I'm really asking just to be nice and helpful. I like questions. Is there something about this part that I should go back to, or I have what about for anything about this?
So just when in doubt, put parentheses over and then put like whatever number on the bottom.
When in doubt.
Or like in a situation like that where you need -3s, but you only have -1, so you put the parentheses and you put the 3 under, symbolizing that you have 3 of the ClO3. 3 of them.
I'm going to say very good, with one little exception, and maybe you meant this, I don't know, but let's just pretend for a minute I had that. Then I don't need a parentheses because this is just one element. I use parentheses for a group. Otherwise, it looks like 33 oxygens and 1 chlorine.
Oh, actually, yeah, I did not see that because, yeah, if it was a group, because there was a 3 under there, and if you just put another 3, it would look weird. Like you had 33 of
Yeah,
the thing.
where there's no confusion on this one. So, I mean, I guess you could put parentheses, but people will stare at you like you're wearing a mohawk haircut or something. Like, really? You put a parentheses there? Okay, weirdo.
Okay, that helps a bit.
I mean, I guess you could. I just don't think I've seen anybody bother. Okay, now that we have this charge is adding to 0, we have something that nature would make. Now, the next probable mistake at this point is to think, I made the product, I'm done. Well, we kicked out the cobalt. Don't forget to write that. And the cobalt gets kicked out. It didn't disappear. You can't just skip it. I mean, it may have, in fact, sometimes we make like CO2 and it's a gas. We didn't really get into this, but G for gas. And it just goes away because it bubbles out of the water and it just kind of goes into the atmosphere. And so it goes away, sort of. But we still write it down because it's still a thing that got made, or, so we don't just skip it because it went away. It may have gone away in practical terms in real life as you watch it. It may go away and be lost and you'll never get it back, but you don't just skip it. Otherwise, it looks like you didn't know it was made. So there's our cobalt got kicked out. And metals just sit there as one thing like the iron did. Now we can put a 4 or a 29 here or whatever, but we're not going to put a number here. So let's balance it. Oh, it is. We're done. No, we're not. No, we're not. I was very wrong. Very wrong. I have 3 sets of chlorate group, and I have 2 sets of chlorate group. I have the classic 3-2 problem. Anybody remember what we're going to do?
Multiply one by 2 and the other by 3.
We're going to multiply this one by 2 and this one by 3. And now I have 6 sets of chlorate, or I have 3 sets of 2 sets. Same thing. I have 2 sets of 3 sets, which is 6. Now, I'm going to say pause. Does that set thing work for you? Because it needs to work. Give it a think. I can say, ask a question, say, I don't get it.
This isn't really a question, but I just want to let you know that I'm going in and out of actually hearing you because my internet connection is so unstable. You either alternately sound like a robot, or it's crashing with about 5 minutes of actually listening to what you're saying.
Okay. If you can hear me right now, I'm also recording this and I'm going to post it on YouTube and put the link on Classroom.
Okay.
Okay. So I have 3 sets of 2 sets of chlorate, which means I've got 6. I've got 2 sets of 3 sets of chlorate, which means I've got 6. And then somebody says, but you messed it up. You messed it up. The scandium worked and now you messed it up. Right. That's what we talked about last time. When you fix one thing, you probably messed up something else. So go and fix that. Just keep working. 2 scandiums come out of this reaction. That means you better put in 2 scandiums. So there's a 2 there. Also, there's one more thing. One more thing to do. This is not entirely correct yet. Anybody?
I don't know.
The cobalt?
as it stands right now, this also is a bit of a lie. It says you put in 3 cobalts and only 1 came out. Well, that can't happen. That's magical thinking again. What happened to the other 2? They disappeared from the universe? No, they didn't. If you put in 3, you get out 3.
Mr. Sweeney,
Yep.
are these all the type of bondings? Not
All the
bondings.
ti-
Reactions.
Are these is this the types of reactions? Is that, can I say that? Is that your question?
On this page, does it
Yeah.
cover all the types of reactions or just the popular ones?
Oh, well, this is these 3 and 2, 5 types are, in a sense, you know what? I didn't even get acid base. It really should be 6. So there are 6 sort of fundamental types, and that's all we're going to get to in an intro class. Yeah. So if you want to add something, you can put acid base reactions into YouTube. We got to get there. I didn't even notice it wasn't on this. Plus, I can't get to it today, obviously. I mean, I can't even get to the other sections. And it's okay that it's taking this long. I would rather get everybody on board the little knowledge choo-choo train here than blast through, say, I got through 5 sections and then have a bunch of Fs. It's not even worthwhile. However, okay, at the moment, I want to do 18. I'm going to go faster, so just partly so I can get it on the recording and then tell you which ones.
We can do 17 since there's multiple answers for that one.
I was actually going to do 18 and just say, you can just pick a charge on iron and put something.
Okay.
Oh, what did I put? Or you know what? Here, let's cheat. You want to look? Let's cheat and use where's my answers? Let's just tell you which one to use. They used iron +3 is what they used. Here, let's use iron, iron +3. There. Then you get the answer on the solution sheet. So if I power through this, aluminum is a positive, a metal. It could attract a negative, okay? And I'm gonna hit the gas here. Aluminum is a +3. Aluminum is a +3. Sulfate is a -2. Sulfate is a -2. Sulfate is a -2. The charges need to add to 0. I have a 3-2 situation here, so I'm going to have 2 of this makes +6, and 3 of that makes -6. Aha. And that doesn't match. You had 3. I know. That actually is fine. Okay. Actually, that one ends up matching. Okay. So the gold, I know that's gold. It doesn't look like gold, but it's from the Latin. The gold gets kicked out and metals just sit by themselves. Double check. -2, 6, +2, 6. Yep. Okay. So then we can balance it left and right. And just pick something that doesn't match. I would leave the gold to last because it's sitting over here. But anyway, 3 sulfates. Oh, that matches. 2 aluminums. Okay. 2 golds. Okay. And just double check. 3 sulfates, 2 aluminums, 2 golds. Yeah, that's it. There we go.
Mr. Sweeney,
Yep.
wouldn't all atoms be alone except for the diatomic ones?
That's partly yeah, kinda. Yeah, I suppose you're right. Metals especially, though. Yeah, the diatomics. Well, okay. Then there's extra weird exceptions that I even have an explanation for. that apparently S likes to exist in groups of 8 for some reason. I mean, I'm not expecting you guys to know that. I was never going to mention it except that you just said that. Oh, I think it came up on one of our sheets. It doesn't even come up in the AP class. So, but yeah, basically you're right. You know what? How about we just try 17? And I'm going to hit the gas again. Use iron 3. Okay, iron is a positive 3. What's it going to grab? The negative thing. But H is +1, so it's not going to grab that. It's going to grab the other part. It's going to grab the PO4. Now, there's 2 ways to discover this charge. This PO4 is stuck to 3 H +1s. So what's its charge? If it's balancing out 3 +1s, it must be -3. Or you could look it up and say, oh, it's -3. So okay, it's -3, -3. Oh, those charges already add to 0. Good for me. Here's the last little trick to that, though. What gets kicked out? The hydrogens. And it's, what's up? Did I hear somebody? Okay. This is the classic, totally easy mistake to make. I'll kick up the hydrogens. And he said the thing that gets kicked out is by itself. No, I said metals. Hydrogen is very much not a metal, and hydrogen has the star, and hydrogen likes to exist in pairs. It's diatomic. It's 2 atomic. It likes to exist in pairs like that, which means I have a 2-3 problem with hydrogen. So let's put a 3 here and a 2 there. But that makes 2-phosphate. It was beautiful. You messed it up. Well, just keep going. 2 of these. So now I have 2 phosphate groups. That messed up the iron. So 2 here. And then, since we have a whole bunch of coefficients, the numbers in front, also you could ask yourself, do I have all even numbers? Because I shouldn't have all even numbers. 2, 2, 2, 3. 3 is odd. I do not have all even numbers. And then, in my last moments, I'm going to say, I greatly recommend, as a matter of fact, I think this is the Friday assignment, is do the ones that we could do, which is that's a synthesis, that's a single replacement, synthesis, synthesis, single replacement, single replacement.
So we don't do the decomposition ones yet?
Hey, if you can figure it out, go ahead. And there are a bunch of rules, but I know from experience that even with those, I had kids staring at me like I was kind of speaking German.
Okay, so
So
those
go
are,
ahead.
yeah, so we don't have to do those. We just need
Right.
to do synthesis
Do you mind
and
to-
single replacement.
Right. I'm just double checking that that's all of them. I hear you. Hold just a moment, whoever's speaking up. Okay, it's those. Those are the single replacement and synthesis ones on here. Okay. And I think that's it. I'm actually going to stop the recording, but if you have more questions, stay on and ask.